question 44 from the GATE 2019 EE paper, where we are given a 3x3 matrix A and B, which is a matrix polynomial expression of matrix A, and we are asked to find out what the determinant of the matrix B is up to 1 decimal place. Underneath the question, you will find the title of the NPTEL course or video relevant to this topic.
So in this question, this is the matrix A, a 3x3 matrix, and B is the following matrix polynomial expression. And we are asked to find out the determinant of B is. So to find the determinant of B, we can use the following method, where we find the eigenvalues of B and determinant P of B is the product of the eigenvalues, right? So the idea is that A has the following Jordan form. How do I know this? Because the eigenvalues of A are 2, minus 1 and 2, or minus 2, 1 and 2. Right? This comes from the fact that A has the following characteristic polynomial, right? You take the determinant of A minus lambda I, and you will get directly actually from the polynomial that the roots are minus 2, 1 and 2. So these are the eigenvalues of A. So if these are the eigenvalues of A, then we can get that A has the following Jordan form, right? And that is, it has the Jordan form TJ inverse, but J has the following matrix. J is the following matrix, right? So now, given that A is equal to TJ T inverse for the following J, we can then substitute for A in the expression for B, right? So you'll get TJ T inverse power 3, TJ T inverse power 2 and so forth, right? And I can be written as T into T inverse, right? So let's just, for example, take out TJ T inverse the whole square. So this is TJ T inverse into TJ T inverse, the whole square, right? So that's 2 of them. Now this into this is I, right? J into I is J, and then J into J is J squared. So this is J squared. So this becomes T J square T inverse. And similarly for Tj and T inverse to the power 3, you will get J cubed. So it's J cubed, J square, J, and so forth. Now you can pull out all the T's pre-multiply the matrices, right? And all the T inverses post-multiply the matrices. In this case, of course, I is this T I T inverse. So you can pull out T as a pre-multiplication and T inverse as a post-multiplication. And this is what you will get as the Jordan form for B. So B is T some matrix T inverse, right? And so therefore this will serve as the Jordan form representation for B. And of course, since J is a diagonal matrix, it's very easy to take the powers of J and subtract. It's very easy to do this expression on J, right? So simply, so J cubed will be, for example, J cubed will be 2 power minus 2 power 3 minus 1 power 3 2 power 3, right? So it's simply this expression on the diagonal entries, right? So this gives us, of course, simplifying this gives us the identity matrix, and so B has the Jordan form I. So its eigenvalues are all ones. That is, it's a diagonal matrix with ones on the main diagonal, so its eigenvalues are all 1. Thus, determinant of B, which is the product of the eigenvalues, right, is equal to 1 into 1 into 1, and that's 1. So the answer that we need is 1. So of course you could have also obtained the eigenvalues of B in a different method. That is, you could have said that if what is the eigenvector for B, right? So let's say B is equal to this and X is an eigenvector of A, right? Let's say X is an eigenvector of A. And what would be B into X? B into X would be this expression into X. Now you can bring X inside here. A cube into X will of course simplify as A square AX. AX is lambda X because X is an eigenvector of A with eigenvalue lambda. And similarly A square will become, so that's for every A power here you would get a lambda here, so that is lambda cube into X is what this first term would simplify to. Similarly, this is A square into X would simplify to lambda square X, and 4AX would become 4 lambda X, and I into X is just X, so that's 5X. So this would be the value. So that is B. Essentially what has happened is B times X is equal to some constant times X. So therefore X is also an eigenvector of B with the following eigenvalue. And we know the eigenvalues of A, so you can just substitute for lambda here and we'll get the eigenvalues of B. Doing so, you will find that the eigenvalues of B are all ones, just the same as the Jordan decomposition method. And similarly, you can just do determinant of B is the product of the eigenvalues and you will get that the answer is 1.